Good morning, Physics 20. I hope you guys are all doing very well today. You guys ready to rock some physics? Oh yeah. So welcome to the new unit. This is the unit on simple harmonic motion and mechanical waves. It is the last unit of Physics 20. And let's get started. All right. So today we're looking at simple harmonic motion with the pun. Did you listen to the debate on simple harmonic motion? It was just a lot of back and forth. Because in simple harmonic motion, the object's going back and forth, back and forth, back and forth. Yeah, had to happen. All right. So, ladies and gentlemen, so with our simple harmonic motion today, it is a motion which repeats itself over and over and over again along the same path because of a restoring force. So be it kinetic energy in gravity, or be it a spring constant in gravity, something like that. So with this one, you can think of a spring where you have an object bouncing on the end of a spring. You could have a swing. So like on a kid, you push a kid on the swing and they go back and forth and back and forth. And in that sense, you also can have pendulums as well in there. Okay, so ladies and gentlemen, if an object is going to have a repeating pattern of motion, so such as simple harmonic motion, the object is also going to have a period and a frequency. So remember how we use period and frequency with our circular motion? Coming back to haunt you again. So period, once again, is the time it takes to make one full circle or one complete pattern. So whatever the pattern is, if it's a pendulum and it's back and forth, the time it takes to go from here to there is the period. The frequency is the number of complete cycles or patterns in 1 second. Okay. All right. All right. So, and remember, ladies and gentlemen, that the period and the frequency are the inverse of each other. Cool beans? Cool beans. All right. So we're going to be focusing on two different types of simple harmonic motion. We are going to be focusing on springs and pendulums. So when we have a spring and a pendulum, and you're going to have one bouncing like this on for a spring and a pendulum swinging back and forth, you are going to have lovely simple harmonic motion. And we can calculate the period of either the spring of an oscillating spring or a swinging pendulum based on our equations. So this guy here, ladies and gentlemen, calculating the period of a spring involves this equation here. Now on your data sheet, you will find these equations right here. So you see where you have the waves section of your data sheet. You have your two equations here, and you also have your period and frequency equation there. So these are the three equations that we're going to be using today. All right. So for this one, M is the mass attached to the spring in kilograms. K is the spring constant, so how stiff the spring is. And T is the period in seconds. Okay. So T equals 2 pi times the square root of M divided by K. So let's have a look at this. Instead of doing a field trip video, because what we're looking at is pretty simple here, I've got all the stuff, demo stuff ready here. Okay, so for this, I have a little D4 or four-sided dice shaped bag, where funnily enough, I keep my dice for D&D. So I've got a bunch of D&D polyhedral dice in there. And I've got, attached to the bag, I have an elastic band. Okay. You know what? I want to try something. Let's see if I can get this to work. Will it let me switch in the middle of a film? Okay, maybe not there. You know what? I think I've discovered something. There we go. I can go full screen. I didn't know that in the middle of a video. So cool. I learned something new today. All right, so this will be easier for you guys to see. So now, notice here, I've got my bag of dice attached to an elastic. I don't have a spring, but fortunately, elastics and springs are going to work in the same fashion for our purposes here today. So I've got two elastic bands that we're going to be looking at. I've got a stiff elastic band, broccoli elastic band, and then a thin one. And we're going to compare the K values, the stiffness of the spring, to the mass, or the number of dice in the bag. So here, I've got a very low K value and a low mass. So when I pull them to get them going, the period is really pretty small. Low mass, low K. It doesn't even oscillate very long before friction stops. So let's change our elastic band and give K a higher value here. So K is going to be large and have a smaller mass. Well, like the period is tiny, like it hardly anything. There's hardly any cycle at all. Okay, so and when you go back and look at your equation, well, that makes sense. Okay, because when you look at your data sheet, okay, you have M over K. Well, low mass, large K, well, you're going to have a smaller value for frequency, or the period, excuse me. Cool, hey? Yeah. So let's shake it up a bit. I'm going to change the mass. So as you guys can observe the change in data. So I've opened up the dice bag and I've got my other dice bag. Yeah, I know I got a lot of dice for D&D. It's a thing. You play Dungeons and Dragons or Pathfinder, or these are actually my Magic the Gathering dice for +1/+1 counters. You need dice for these games. So you're going to increase the mass by adding all of these dice here from this bag into this one to increase my mass. Sorry. So you guys can see how we're changing our variables to compare them. Okay. There we go. I've filled this thing with dice. Okay. Whoops. Get back in there. Escape of the D10 and the D6. Okay. There we go. I cannot get any more dice into that little bag here. So I now have a much larger mass, but the K is still my large K value. Okay. So I'm now going to oscillate. Oh, look at that. We're actually getting some more oscillation here. And the period is longer. It's taking longer to do one complete cycle because the cycle is actually larger. Let's switch back to our other elastic band. So the one that has low K for our spring constant. All right, so now this one, I would expect my period to be the largest. So when you look at your equation, it's M over K. So I'm going to have a larger value as my numerator and a smaller value as my denominator, which in the end, if everything else all being equal, I should have a larger period. Okay, there we go. Awesome, hey? So that's why those values are the ones that are significant to the equation. Cool beans? Cool beans. Okay, I'm going to jump back down to the corner of the screen so we can go look at our next equation. There we go! I'm back in the corner of the screen. This is so cool. I'm learning tech all the time. I wish I'd learned this in back when the schools closed in March and it's June now. So, oh well. Live and learn. You know me in technology. We're lucky I actually have been able to film stuff. and I'd only break the internet once. Okay, so ladies and gentlemen, that's how our spring equations for simple harmonic motion works. And now we're going to be looking at how to calculate the period of a pendulum. Note the equation is very, very similar. However, we have, so T is the period in seconds. Now, G is the acceleration due to gravity. So most of the time, we're going to be near the surface of the Earth. Very rarely are you yourself going to be hopping up into space, orbit Earth and to swing a pendulum just to do this equation. So assume unless told otherwise that you are close to the surface of the Earth, and now you can just go back to using 9.81. Okay, unless I tell you differently. L is the length of the pendulum. So the value of the length of the pendulum is here. From here to here, or here to here. Well, notice, ladies and gentlemen, with t equals 2 pi root L over g, there's no mass. Well, doesn't the mass impact the period of the pendulum? No, it doesn't. It impacts the kinetic energy, it impacts the gravitational potential energy, but it doesn't impact the period. So we're going to demonstrate this for you. I've got my keys. I'm going to go full screen again. Use my awesomely discovered new tech. Yeah, we're full screen. Okay, so I've got some keys. I've got my school keys, okay, and got lanyard. Yeah, I don't know if he showed up. See? Little St. Joe's. Isn't he cute? A little type of keychain called Tiny Saints. I think they're adorable. Okay, so I've got my pendulum of keys, and I've got camper trailer keys, and I have absolutely no idea what these keys are for. I have no idea. I just found them lying around, so they're in the key drawer, so, or bowl, whatever you want to call it. Okay, so we're going to compare the length, and we're also going to look at the mass. Sadly, I can't launch into orbit for the sake of this video. You know, budget cuts, yeah, prevent actually going into space to demonstrate stuff. So we can't actually compare the differences of different G values. I know, right? Okay, so we're going to start with the length of the pendulum, and then we're going to change the mass just so you can see that it doesn't change anything with the period. Okay, so we're going to start with full length. I'm going to go backwards a bit so you guys can actually see this better. So you guys can see mobile in the back is kind of where the keys are at. Okay, so you guys can see the motion of the pendulum there. All right, now let's shorten the length. Okay, and now let's compare the period, so the time it takes to go from one and back. Okay, so I've shortened the length by pulling the keys in. Notice the period is a lot faster now. So the shorter the length, the shorter the period. Cool, hey? Well, let's just show that mass doesn't affect this. So I'm going to increase the mass of the pendulum bob. So when you see a pendulum bob, you're talking about the object on the bottom. So I'm going to put those keys on to my school key ring, and I'm going to put these keys on. So now I have increased the mass significantly. I'm so glad I do not have to carry keys around like this. Although, if you ever see Chester's keys, he's got keys like this. Like, Chester can open every door that ever existed in the school. No. So we're going to go back to our full-length pendulum here, and I want you to observe and compare what the period looks like. It's the same as it was with only the one set of keys. Let's go and compare it again. So I'm going to take off the 2 extra sets of keys there, and we're going to swing it again. Okay, the value is the same. Okay, so you can even just visually see that like, we could calculate it if we wanted to, but the period itself is the same regardless of the mass of the keys. So that's why mass is not actually included in your calculation. Cool, hey? I think it's pretty cool. All right, let's go back to, there you go, I'm back in the corner of the screen again. Cool. All right. So, ladies and gentlemen, let's look at our graphs, and then we will look at, our practice problems. All right, so sketch the shapes of the following graphs. So remember, ladies and gentlemen, that what we do is we rearrange our equations so that way it looks to be similar to our y equals mx plus b. So our y-axis needs to be isolated. So for the period here, the period is equal to of our spring. So with spring, we've got our 2 pi times the root of m over k. So, ladies and gentlemen, we are comparing the the period, and the mass. So remember from our demonstration earlier, what happened to the period when we increased the mass? Well, it increased. So I am going to make absolutely everything else equivalent. Okay. So I am going to have, that's all the same. Oopsie. Oh, come on. Sorry, guys, this thing stopped working. Give me a sec to sort my tech issues, and I'll be right back. I'm just going to pause the video. All right, I think I've got my tech problem sorted. Let's hope, actually, that happened. All right. So, ladies and gentlemen, when we are going to take this and make everything else in our equation equal to 1, our t is going to be proportionate to what with the mass? Root of m. Okay, so t is going to be proportionate to the square root of m. Well, when we go back at our notes, you will see that this pattern is similar to y is equal to root m. Okay, so what we're going to see is a graph pattern that's going to look kind of like that. Okay, so you can, as we increase the mass initially, you are going to see an increase in the period. However, you are eventually going to hit a point where with that same spring, you can increase the mass and the period is no longer going to change. Okay, so similar, if I was able to add more and more dice into that dice bag, eventually the period would taper off. Sounds good? Okay, well, now this one we have a pendulum. So we're going to be comparing mass of period, mass and period in a pendulum. Well, let's look at our equation. T is equal to 2 pi times root L over G. Well, look at your equation. Remember what we talked about earlier when I was full screen and demonstrating mass? They aren't related. So, ladies and gentlemen, the period is not proportional to mass at all. Okay, and mass isn't in this equation. So therefore, as I increase the mass, the period is going to stay the same. The mass does not impact the period in a pendulum, whereas it does in a spring. Sounds good, guys? All right. Okie dokie. Are you guys ready to roll for some calculations? Yeah? Okay, cool. So for this, ladies and gentlemen, if the bob of a pendulum has a mass of 0.25 kilograms, if the pendulum is 1 meter long, what is its frequency? Okay, well, we have the mass of 0.25 kilograms and we have our length of 1 meter long. And we have been asked to calculate the frequency. So what can you tell us about these numbers here? What is significant about that 0.25? Distraction. You don't need the mass. The mass is 100% a distraction. Complete distractor. How rude of it, right? All right. So, ladies and gentlemen, well, I need the frequency. Well, when I look at my equation of my t is equal to 2 pi root length over g, well, there's no frequency. But I need the frequency, so what do? I find the period, and 1 over the period is equal to the frequency. So that's going to be my first step, and this is going to be my second step. Okay, so the first thing, the period is 2 pi times root L over G, and then 2 pi times the root of the length of 1 over 9.81. All right, so calculator time. So ladies and gentlemen, when you're putting this into your calculator, follow this order. Okay, so please start with, okay, 1 over 9.81. Enter. second square root second answer. Enter. Times 2 times second and then pi. If you put in 3.14 in your calculator, I will be upset and sad and cry inside. Okay? So once you put that into your calculator correctly, you're going to have 2.006 ... seconds. Well, we're looking for the frequency, so we go on to our second step. The frequency is equal to the inverse of the period. So the frequency is 1 over 2.006 ... seconds. I want to show you guys a trick. For your calculator, you've got a couple of different options. So you could 100% go 1 and then divided by your second and then answer. You're 100% welcome to do that. Or what you can also do, 2.006, I've deleted this from my calculator so I can't use all the digits here. I want to show you a trick. You guys see this button here? That x to the power of -1 right here? Push that. So I've got 2.006. I push the power of -1 and then I hit enter. Guess what? It's exactly the same value as if you go 1 over second answer. The power of -1 is the exact same thing as 1 divided by. Okay, so that's just a shortcut for you. That might make your life easier. All right. So, ladies and gentlemen, once you get our frequency of 0.4984 ... we need to put this in appropriate sig digs. I have 2 sig digs, and so I round this to 0.50 hertz. Sounds good, guys? Cool. All right. There we go. So, our next question. A horizontal spring has a mass of 1.5 kilograms. Okay, now we need our mass attached to one end and the other end is secured to a wall. A force of 25 newtons is used to compress the spring. Okay, so compress the spring, 25 newtons is used to compress the spring. We see what's happening here. A value of 16.5 centimeters. What is the period of the spring? Well, ladies and gentlemen, we need to find, when we're finding the period of an oscillating spring, our equation is 2 pi root m over k. Well, I have m, we got 2 and we got pi. Well, we need k. How do I get k? Use your spring equation. So our spring equation, remember, ladies and gentlemen, our force is equal to kx. So I'm going to use this equation first, and then I will use this equation second in order to get the period. All right, so the first thing I have, my email is going crazy again today. So F is equal to kx. I will rearrange this to get k. So k is equal to F divided by x. And I will plonk those numbers in. So I've got my, where'd it go? 25 newtons divided by 1.5 kilograms is going to give you a spring constant of 151.51 repeating newtons per meter. I will then take this number up here and put it in this equation. Okay. All right, so the mass is 1.5 kilograms. And K is here. Use all values in your calculator. There we go. All right, so when you put this in your calculator, so 1.5 divided by second answer to get the full value of this, enter. Second square root second answer, enter. Times 2 times second pi, enter. That's how you got to put her in the calculator, all right? All right, so the period, ladies and gentlemen, is 0.62515 ... seconds. All right, sig digs, 1 point is 3 there, 3 there, 3 there. Okay. So, ladies and gentlemen, I just realized I did a silly thing. I wrote my numbers down wrong. Okay, before I put this into sig digs and units, I want to go back and fix my mistake. I wrote down 1.5 kilograms here. That was a whoopsie. What I needed to do was first I needed to convert this into meters. Okay, I didn't put the 16.5 when I did this. I actually put in the 0.165 meters. I just wrote it down wrong here. Oops. So this is the value that you are going to put in here. So the 0.165 meters there. So don't forget to convert your units. This answer is still going to be the same, but wrote it down wrong. Can't even blame Monday. We'll blame Monday even though it's actually Wednesday. So Monday's fault. Okay, now sig digs and units. So with this, we've got a period of 0.625 seconds. Sounds good, guys? All right. So, ladies and gentlemen, we have one more question to do, and that will be today's lesson. All right. So, ladies and gentlemen, a vertical spring with a 575 gram mass on the end. So it's a spring, so we do need mass. I'm going to convert this into kilograms right now. I am not even going to wait to do that. Just convert that to kilograms. Okay. And is stretched 15 centimeters from its equilibrium position and then released. Okay. So I am going to actually remember to write down the conversion of units here. So I'm going to convert this into meters right off the bat. More email, goodness. And assume an isolated system, so assuming no energy lost from friction. Calculate the mechanical energy of the system if the spring is a period of 1.2 seconds. Okay, this is a toughie, ladies and gentlemen. So, ladies and gentlemen, let us think for a moment. Okay, so we have period that we are looking for. Okay, we've been given the period. So, however, what are we missing here? Calculate the mechanical energy of the system. So that means we want the sum of all energies. Well, ladies and gentlemen, let's think about this for a sec. Mechanical energy is equal to the potential energy at any point plus the kinetic energy at any point. Well, let's do this the easy way. Let's go with maximum spring elastic potential energy. The sum of the maximum elastic potential energy will always equal the total energy throughout the system. So I'm going to go to a point where my kinetic energy is 0. So that would mean my mechanical energy is going to equal EP. So the spring potential energy. Well, thinking back to our previous unit, I know these equations come back to haunt you. Our mechanical energy, our elastic potential energy equation is equal to 1/2, that's kx squared. That's an x. 1/2 kx squared. Okay. So, well, what we have here, ladies and gentlemen, is, well, I have x. I've got the value of x here. Okay, so that's good. Well, problem is I don't have k. How can I get k? I've got the period. So what I could do, well, the period is equal to 2 pi times root m over k. Well, look at that, ladies and gentlemen. I can rearrange this to get k. So the first thing that I'm going to have to do here is this. The second thing is this. Sounds good? Okay. So, now this is a really tough question, ladies and gentlemen. So if you're having any issues with it, make sure you sign up on Google Meet there so we can go through the question. All right. So, ladies and gentlemen, we've got period is equal to 2 pi times root m over k. Well, I'm going to have to rearrange this in order to get k. Oh, tricky, tricky. So the first thing I'm going to do is I'm going to divide by 2 pi. So root m over k is going to equal period divided by 2 pi. Okay, so divide both sides by 2 pi. All right, I'm going to have to scroll down a bit here. I'm running out of space. There we go. Okay, so, well, I might get rid of the square root before I do anything else. So what I'm going to do for that is I'm going to square. I'm going to square both sides because squaring is the opposite of square root. Okay, so those guys cancel. So I am left with m over k is equal to period over 2 pi squared. Okay, so ladies and gentlemen, what I am going to need to do is rearrange this to get k on its own. So what I'm going to do is I'm going to do my shortcut and I'm going to swap these. Okay, I'm going to swap this whole thing with that k. All right, so k is going to equal m divided by t over 2 pi squared. I know, it's kind of nutty looking. So with this one, you're gonna have to be super careful with putting this in your calculator. Okay, so the mass, ladies and gentlemen, is 0.575 divided by the period, which is 1.25 seconds, divided by 2 pi squared. Okay, when you put this in your calculator, I would solve for the bottom first. 1.25 divided by 2 second pi, enter. Square, which will be answer squared, enter. 0.575 divided by second answer, enter. Sounds good? Good. Okay, I'm going to scroll down again. And I'm going to get my value of k to be 15.7639 newtons per meter. Okay, I'm going to scroll up a little bit here. There. All right. So now we're going to go on to our second step. So our second step is because our mechanical energy is going to equal our maximum potential energy. Okay, so ladies and gentlemen, my second step, as we derived right here, our mechanical energy of the system is going to equal 1/2 kx squared. Okay, so I am going to use my value of k here. So 1/2 times the value of k, which is what, 15 point, let's put my decimal in the wrong spot. So 15.7639 times the value of x, which is our 0.15 meters. Don't forget to square x. So the mechanical energy of the system is going to equal this elastic potential energy of the spring, and with your sig digs and units and all that good stuff is going to be 0.18 joules. Sounds good, guys? Okay, this was a really tough one. I know that one's pretty tricky. All right, so ladies and gentlemen, that's it for today. We got some practice problems there for you guys to take a crack at in your workbooks, and then we've also got some practice problems there for you. All right, sounds good, ladies and gentlemen. Cool beans. You guys had fun? Oh yeah, physics rocks. All right, so ladies and gentlemen, I hope you guys have a good rest of your day. No fires, injuries, or explosions. Talk to you later. Bye.